Hello everyone, in this video we will take a look how to create parallel processing, parallel calculations in Minix, especially by taking into account C language by using a CLang compiler. So what we're going to take a look today at, so we can refer to an operating system design and implementation book written mostly by the Tannenbaum, who exactly created the Minix system. Okay, so here we can see the mass code of this operating system. So that's the Linux with basic functionalities, which are definitely implemented in most of the Unix type operating systems. So what we're going to take a look today at. If we will take a look on the ways how we can run calculations, we can run them in two ways, and both of them dependent on the kernel. And kernel is the basic app of the operating system. And there are two ways how to run parallel processing in the Unix. And actually the same happens in Windows operating system as well. So there are two ways to create exactly parallel processes, and each of these processes will run just one executional thread. So what is the executional thread? The executional thread is the chain of operations that happen, that are being calculated one after another one. So all code we write in the app basically contain a lot of operations, and those operations are just structured in a chain, and this chain of operations is being given to a CPU for running each operation separately, one after another one. There are two ways of running such parallel executions. We can create few processes, and all of those processes will be run simultaneously, or we can have one process, and one process can contain a couple of executional threads. So what does it mean? It means there are a few chains of instructions, and all of them are being run or executed simultaneously. So what does it really means? Let's say we have a couple of instructions which should be run simultaneously. What does it mean? It means that one operation will be given to CPU, then another one, then another one. Okay, about this it's clear that CPU can operate only with one operation simultaneously. And a couple of chains of instruction basically means that we take one operation from one chain, then we take operation from another chain. Once again, we take operation from one chain and then take operation from another chain. And actually it's fine, but there is a huge difference between these two ways of running the app. And in this video we'll take a look exactly on multi-process execution way. Okay, so what functionalities, which C language functions we will use this time? We will use specialized functions, once again mentioned in this book. So we will use the fork function that basically creates a child process. So we can create a tree of processes where we can have the parent process and the child process. So fork function creates a child process. And the idea is that besides the fact we create the child process, the parent process can be finished faster, and it doesn't automatically mean that the child process is being finished as well. No, it doesn't happen in this way. And we will take a look on a couple of your functions. So probably we'll take a look on wait for process ID. So we will wait until the child process will be finished. And we will try to take a look on the process ID, so process identifier, because process identifiers are being changed once we create a child process. Alright, so let's start with taking a look at the Minix system. Alright, so right now we see the Minix logon screen, so as regularly we type root password. Alright, so we are inside our system. Let's create the folder AAA, and let's go inside this AAA folder. Okay, so we have no files here, and as a regularly in Unix systems, so we can create files by using touch operation. So I'm going to use touch operation to create a file. Okay, so in this case I'm going to create the file multiprocess.c. So I will just make the name smaller, multi-pr, so it will mean basically multiprocess. Okay, so we have multiprocess.c file, so we have to be able to say it, and I will use the nano editor to edit this file in the terminal, because basically there are a couple of different editors, but for me the best one is the nano, at least at this point. So that's why I'm just going to use exactly nano editor. Okay, so I type nano multi-pr.c, and we have this editor open on the screen so we can write codes. Right, so what we are going to do, so from the very beginning we are going to just create a simplified application. So let's create the app that basically prints out some information on the screen. So I will use stdio library, and I will use a specialized library which should be used for parallel processing, at least in the Minix system, and actually in most cases it happens in the same way for other Unix core systems. Okay, so I use unistd.h library, and I'm going to create int main function. So int main assumes that I'm returning the value. For example, by default I will return value 0, and it's totally fine. What happens afterwards? Afterwards I'm going to create integer typed variable PID. Basically PID will receive identifier of the process. So each process which has been launched within the operating system has its own identifier. Definitely when we run the process which is actually being created as the child process, it always receives identifier equal to a 0, and once child process becomes the parent process, it receives its natural number identifier, which is not equal to a 0. Right, so let's make some printout on the screen. Let's say I'm going to print out 111, and I'm not forgetting about the new line symbol. Alright, so I'm having printf 111 on the screen. Then I'm going to save this file, compile it, and try to run it, just to take a look that everything's fine, at least at this point. Alright, so what I'm going to do, I'm going to press Ctrl O just to rewrite the file, and I'm pressing Ctrl X just to leave the editor. So as you can see, we can just work with the terminal commands as we worked previously. So what I'm going to do, I'm going to compile the file. So I'm using clang compiler. I'm mentioning multi-pr.out as executable file's name, and I'm mentioning multi-prc as the source file. Alright, so right now compilation process is happening, so we have to wait for a couple of seconds. Okay, so that's fine, and we have to take a look how's it going with this application running. Okay, so I'm going to run multi-pr.out file. Okay, and we have a 111 on the screen. This fine. So at this moment I'm going to create the child process. So once the child process is being created, so once child process is being created, its identifier will be written into a variable which we assign the fork value for. Okay, so literally what's happening here? I write PID equal to a fork, and fork creates a child process. And afterwards, I'm going to print out a 222, once again with the new line symbol. Okay, so what will happen right now? Let's write file, let's exit the editor, let's compile it, and let's run it. Okay, so literally we have once 111 and twice 222. What happens? It happens because exactly on that line PID equal to fork, we create the child process, and both of the processes, I mean the parent process and child process, are being executed exactly with the next comment standing after the fork function. So it means the part which stands in the code before the fork function is being already executed, so it's not going to be run once again. And what literally happens at this point? At this point, literally, operating system takes our application values, actually the whole memory which was created within the application, and makes its clone in the RAM. Okay, so let me open Office Calc so I can show it a bit visually. Definitely that would help us. So let's say we have a couple of instructions within our application. For example, a equal to 7. Then let's say we have okay, here we have a equal to 7 operation. That will be the first one. Second will be a is equal to a plus 1. For example, next operation will be, let's say b equal to 5. Then we would have or maybe let's say b equal to PID. Nextly we will have let's say a equal to a plus b operations. Okay, and let's say we have fork operations somewhere in the middle. For example, here we have the fork operation. Okay, and we have the process 1, which will be the main process from the very beginning. So literally we have two processes. Okay, the PR and PR1 and PR2, and we can write here results. What we have? Okay, so a is equal to 7. Result is 7. Here, what do we have? Here we have result 8. And once fork is being executed, we have this 7 and 8 just copied from the first process. So we can highlight them by using some another color. Let's say the blue color. So these values are just copied from here, and then fork operation creates different PIDs. So here we have one PID, here we will have another PID value. Right, fine. So at this point these PIDs are different. They are just being created as variables within each process. So literally all variables which have been mentioned in the process 1 were just copied into process 2 with values, with data types, and with all other things. Okay, so PID is different. What happens next? Nextly we have b equal to PID, and let's say okay, let me maybe rewrite this equation. PID equal to a fork, and let's say here we will have some 5 value, and here we will have 0. Literally, since b is separated for the process 1 and process 2, the b are different variables. So here we will have b equal to a 5, and for the process 2 we will have b equal to a 0. Next we have a equal to a plus b, and since a is variable, so we have one variable a for the process 1 and another variable a for the process number 2. So what do we have here? We have 8 plus 5, so in the end we have 13. Okay, so we have 13, and a is equal to a plus b for the process 1 will be 8 plus 0, so result will be 8. So literally, what variables do we have? We have a variables for process 1, process 2. We have PID variables for process 1, process 2, and we have B variables, and they are separated. But once we create a child process, so we copy the whole memory which is taken by our process for the child process, and execution cursor is being copied as well. So the next operation which is going to be run after the fork operation will be same for process 1 and process 2. That's the way how it works. Okay, I hope that's clear. So let's go back to the minix system and let's try to work with PIDs, and let's try to run the same operations or similar operations we had in OpenOffice file I just showed you. So let's go back to the multipr.c file and let's create additional variable. So we have PID right now, and let's create A and B variables. Alright, so before the fork operation, we will have a variable equal to a 7. Okay, so A will be equal to a 7. And next we will run another operation, so A is equal to A plus 1. That's great. Nextly, let's print out this variable on the screen. So we have A is equal to natural number mask, and we will place the A variable's value within this mask value. Alright, and after the fork execution we will have another operation. So we will work on the B variable. So B will be equal to PID and A will be equal to A plus B. So let's run these operations. So B is equal to PID, and let's print it out. So we have B equal to natural number mask, and here we will place natural number value. Next we'll run another operation. A is equal to A plus B, and we'll print out this value as well. So we will have A is equal, or let's make it different. A plus B is equal to natural number mask, and let's place new A value here. Since we're not going to work with a variable anymore, at least within this example, it's fine just to place here a variable's value, because it was previously calculated. Okay, fine. So let's overwrite the file, let's exit it, let's try to compile it and run it. Okay, so we have multipr.out, let's run it. So what do we have? We have A equal to 8, which actually happens on each process. Then we have B equal to 0, and it comes from the child process. And we have B equal to natural number identifiers, which actually means that's the parent process. And actually we have two equations, A plus B, which is calculated on each process separately. So we have A plus B on the child process, and its result is 8. So 8 plus 0, and we have 8 plus B, which was calculated on the parent process, and we have 8 plus 247. The result is 255. So that's the good example, and that's the pure example how we can create a parallel processes, and these processes work within one code. So besides the fact that we have a couple of processes, we have one source file that characterizes each of those processes. And since we have these processes and we run them simultaneously, we can program even a way how to operate with them, how to make a communications between a couple of processes. And why is it needed? Well, actually that's needed only because of one purpose. We create the parallel processes only with one key idea, just to reduce the amount of operations which should be run in absolute time. What does it mean? It means if we have two threads on our CPU, then we can split our operations between those two threads. What does it literally mean? It literally means that half of our operations in our application will be run on one thread and another half will be run on another CPU thread. And overall it will make our operation working faster, approximately twice faster. Not always it happens just twice faster, or times or fastening times is equal to amount of CPU threads. No, it doesn't work in this way. Each next additionally attached CPU thread in calculations reduces the efficiency of that new additional CPU thread. And it happens that sometimes there is no necessity to add additional CPU threads in calculations. And even sometimes, in critical situations, it happens sometimes that even, but that we will have to wait even a bit more longer than if we wouldn't attach new CPU threads. So my recommendation would be not to use more than 4 threads simultaneously. But once again, it depends on the task we are solving. If we solve a huge task, so for example, physical mathematical problems, then definitely we have to attach a lot of CPU threads, a lot of calculational units. Okay, so that's the way how we can create the parallel process, and that we have the memory copied from the main process to a child process. And then we start instruction execution right after fork instruction for both processes. Okay, actually that's great, but here we can even take a look how to make a communication between these processes. So let's take a look on how it could happen. Alright, from the very beginning, let's open our multi-PR file, and let's say we will have some calculations. For example, this a is equal to a plus b, and we would need to give this value back from the child process to the main process. So how could it happen? Well, definitely there are a few ways how we can make communication between processes, and the most simple way is to finish the process and give back the numerical result. And definitely this time we will take a look exactly on this method. Alright, so before we take a look on that, it will be really great to take a look, prove that those processes we run, the parent process and child process, are really simultaneous process with the same priority. Okay, so in this case, if only we have these calculations happen, we can even split functionality between the process. So how it could happen? Well, since PID is characterizing factor that basically makes it clear if it's parent process or child process, we can split operations depending on this PID. And in case of PID is equal to A0, we run child process, and in case of PID is not equal to A0, we actually run the parent process. So PID is greater than 0, then we have the parent process. And there could be even another case when PID is equal to -1. It means that it was impossible to create the child process. It could happen because of a lot of different factors, but the thing which we are going to take a look in this case, that we have to print out that there was some fork problem, like this fork problem. And since our app is going to be designed for exactly working with parent and child process, we are going to go out from our software and give the execution cursor to operating system. Okay, so we have returned 0. Okay, well that's great. So if there are some problem happens, so we terminate application. If it's not so, we continue running the app. Okay, so let's say the child process is going to okay, so if we have PID, we are going to if we have PID equal to 0, we are going to let's say print out some information, for example child process, in this way, and we are going, for example, to wait for a couple of seconds. For example, we are going to wait for 5 seconds. But in case when we are inside the parent process, so when our process has PID greater, where value is greater than 0, then we have the parent process, and we are going to say it to a user. So we have the parent process, and what will happen in this case? Let's take a look. We will write the file. We are going out from the file. We are compiling file. Okay, we have some problem. Okay, that's problem related to a text. Okay, great. And then what we are going to do? We are going to run this software, and what do we have? We have child process, we have parent process. So those prints out a file. Fine. Okay, that's great. But since we had a sleep function, so if we would have some printout after the sleep, what we'll get in the end? So we have child process end. So let's say child process executed some operations, and what happens in this way? Okay, so we have child process, parent process, but we don't have child process end. So after some seconds we will have it. So we have child process end. Well, that's great. And why do we have this symbol here that represents the terminal command? So terminal launched one process, and once it receives one process finishing, it just assumes that we can run another terminal command. Exactly, that's why we have this symbol, and that's why it looks like terminal asks us to make some instruction input to execute another operation we would like to execute. Okay, so exactly that's why it happens. All right. So let's work with this. With this. Alright, so here we have our application code, our source code in C language, and we have waiting procedure, which simulates some working procedure on the child process, and we have the parent process, which regularly is being used as the interface process. So pretty regularly we have interface process, which is parent process, and the child process operates with some data, makes some additional work. Okay, so let's create a waiting procedure on the parent process side. For this process, we'll create additional variables. So one of them will be status of the child process. Another will be the process, the child process identifier, which will be received from the parent process side. So PIDC, which will be let's say -1, or let's say there won't be any initial value. Okay, and let's say when the child process will be finished, it will give back some numeric value. Let's say 97, for example. So the parent process should be waiting until the child process will be added and should receive this number 97. So let's implement this on the parent process side. So we have parent process. Let's create another printout printf parent process and the same as we created it for the child process. So parent process and we're not forgetting about the new line symbol. Okay, and in between of those printouts we'll create waiting procedure. So we can use a wait process ID to receive information about the process, if it's running or not running. In this case, a wait process ID exactly receives information from the child process. So that's why to receive information from child process we have to run that function from the parent process. So we will receive this information a couple of times, and actually we will do this continuously a lot of times until or let's say while the process will have running state. So in other words, PIDC will be equal to 0. That basically means that process is working. In other words, it's running. So what do we do here? So we write PIDC is equal to wait process ID, and we mention the parent process identifier. Then we place a status variable that will help us to receive that 97 number, the return number, and we will say that we are not going to freeze our application. So no hang will be the parameter of wait PID function, and that would be great. So that's fine. And nextly, depending on the PIDC value and status value, so we can say that that process was terminated, it's running, or it was finished. And when it's finished successfully with the finished code or unsuccessfully. Alright, so let's create couple of ifs. Couple of if statements. So PIDC is less than 0. In this case, it will mean that process was terminated, so something wrong happened. So printf child process was terminated. Okay, fine. So that's great. If the process is still running, we'll play this information. So PIDC is equal to a 0. Then process is running, so we are writing child process is running. Okay, and if its natural value, which is greater than 0, it means process is finished. And in this case, there could be a couple of possibilities. If the process is finished correctly or incorrectly, in other words, successfully or unsuccessfully. Right. And in this case, we can make a check of the status value. Okay, so we will use W if exited from the status. So we will get the understanding if the process was finished by exiting the process by using the return, or it was finished unsuccessfully with some exception, for example. Okay, and in this case, the process was finished with the value, and we will receive the value. So we are going to write child process exited with value, and we will have the natural number of the exited value, which is actually the value that stands right after the return, this 97. Okay, so here we write W exited, so exit status, and we have to mention the status variable once again here. Okay, that's great. And there is even another scenario when the process was not finished, but finished successfully, but was finished unsuccessfully. In this case, we will have another printout. So printf child process did not exit successfully. Alright, in this case, we just implemented waiting procedure. Basically, it's continuous check procedure of what's happening with the child process. If it's terminated, we have information it's terminated. If it's running, we have information that it's running, and we check it once and once again using do while loop. If it's finished, then PIDC will be greater than 0, and we will be able to take values of the return. So it means we will receive given back values. Okay, so let's save this file. Let's exit it. Let's compile it using a clang. So clang -o multipr.out, it will be executable file's name, and multipr.c is the source file. Alright, so let's compile it and let's try to run it. Okay, so I have problems with functions and constants. Okay, fine. In this case, it means that I have to add additional libraries to my code. Okay, so let me do this. So I'm writing include system types.h. Okay, let's figure out if it's fine right now. Okay, it's still not fine. Let's include another library, so system wait.h library. Okay, hope it will help. Okay, yes, that helped. So sometimes we have to work on a library attaching to the source. Okay, fine. So let's try to run the file, the executable file. So multipr.out. Okay, so we see that process is running, and this printout happens through the main process, through the parent process. So we're waiting for approximately 10 seconds, and what do we have? We have the end of the child process. So we have that child process ended. This printout happened from the child process, and while this printout was happening, the check of what's happening with the child process was in the progress. So that's why we have child process, and in simultaneously we have couple of checks what happened with the child process, is if it's running or not running. That's why after the child process end we have these printouts, because these two processes happen in parallel way. They have been run in a parallel way, and we see information that child process is exited with the value 97. And we have in a printout that that's the end of the main process, the parent process. So at this printout moment, the child process is being finished, and we can finish the main process to give the execution cursor to a terminal. Okay, and what specific things we have? We have this terminal symbol right after the parent process was finished, not when child process was finished. Okay, and we have the value 97, so we have exact value which was received from the child process. So child process returned this value, and we took this value, and then we can manage our app depending on this value. Okay, so in this video we took a look how to wait until the child process will be finished, how to create child process, how to separate operations between child process and the parent process, and how to organize waiting procedure until the child process will be finished with taking the child process return value, and then definitely we can operate with this value somehow, so we can manage our app logic dependent on this value. Okay, so thanks for watching. Don't forget to subscribe and write the comments. And in the next video we will take a look how to make a pure communication between processes, between parallel processes, using streams. So that method will allow it to make a pure communication between processes without finishing them. But this will be in the next video. Okay, so thanks for watching, and see you on the next video.